Welcome back. In this video, we look at neural networks. The idea for neural networks has been around since the 1950s, the early days of AI. You hear a lot more about neural networks today for a couple of reasons. One is that processing power has increased, and the other reason is that larger data is more widely available. Neural networks generally won't outperform simpler algorithms on small data. It's only when the data gets larger that neural networks start to shine. Here is the original conception of the neuron in a neural network called a perceptron. In this example, there are two features, x1 and x2, and each feature has its own weight, w1 and w2. The activation within the neuron is a step activation. If the sum of the weights times their features is over a certain threshold, the output will be 1, otherwise it's 0. Neural networks, also called artificial neural networks, ANNs, are not like the human brain, but they were inspired by biological neural networks in mammals. People often say that deep neural networks act like the human brain. That's a gross overreach. The human brain has about 100 billion neurons. Each neuron is connected to 1,000 or more other neurons. Obviously, we don't have such massively parallel computer architecture at our disposal. In the brain, each neuron has multiple inputs that receive signals from other neurons. When the combined inputs reach a certain threshold, the neuron fires, sending signals out to connected neurons. We don't fully understand how the human brain learns from these interconnected neurons. Despite the overhype, neural networks are very powerful algorithms. Here's a conceptual diagram of a neural network, often called a feed-forward network, because the variables and weights are calculated left to right, going forward through the network. Reading through the network left to right, we see 5 input nodes in yellow. These would be our features of our data. Then we have 2 hidden layers. The first hidden layer has 4 nodes, or neurons. The second hidden layer has 3. Finally, we have a single output layer. Neural networks can be used for either classification or regression. Notice that each node's output is input to every node in the next layer. It's deeply connected. Each of these connections that you see in the black lines here within the network will have a weight associated with them, and that's what's learned in training. Furthermore, each hidden layer as well as the output layer, can have a different activation function. Let's say this node has a sigmoid activation function. In effect, this one neuron is acting like a mini logistic regression function, but it's vastly connected to other functions. And each node in the hidden layers can be learning something different from the input, so that the network is essentially a composition of functions. This complex architecture is what makes neural networks powerful enough to learn complex functions. In the next video, we'll talk about deep neural networks, and all that means is that we have many more hidden layers. The most important decision when building a neural network is its architecture, sometimes called its topology. The input and output layers should be fairly intuitive for a given problem, but designing the hidden layers is challenging. How many hidden layers? How many nodes in each hidden layer? Having too few hidden nodes may result in underfitting, while having too many may result in overfitting. Here are a few rules of thumb to help you design the best network. These rules of thumb just really give you a starting point. One suggestion is between 1 and the number of predictors. Another is 2/3 of the input layer size, that's the number of your predictors, plus the output layer size. And another is less than twice the input layer size. Again, these are just suggestions. This diagram was created in R in a package that displays the learned weights, and that's why I'm displaying it here. This was a housing data set, and this was a regression task. There were 13 input variables, 13 features, and 1 linear output. Following the recommendations that we just talked about, I decided to try 9 hidden nodes. And I got pretty good results by dividing them into 2 layers. When I had all 9 nodes in one layer, the neural network underperformed compared to just simple linear regression. Another thing you want to do when you're building a network is to always have subsequent layers either have the same or fewer numbers of nodes. So we went from 6 to 3 to 1. If you go the opposite direction, you'll just be creating a bottleneck. Sometimes one hidden layer is enough. If the data is linearly separable, one layer should work fine. But having 2 layers can capture more complex relationships between the inputs and the output, at the cost of extra training time. It's usually best to start with a simple architecture and then gradually build it up, and in that way you can avoid overfitting. So how does a network learn? We can see that this network learned weights for all of the connections. Notice also in blue that each neuron has a bias term with its own weight as well. In the feed-forward network, each node is multiplied by its weight, and that feeds forward until we get the final output. This is just basic matrix multiplication, which is highly optimized in modern computers. Once a given node or neuron receives all of its inputs, the activation function kicks in and causes it to output its results. So far we haven't described any learning, we've just described the feed-forward mechanism. The weights are initially random, just a random guess. So as it goes through on the first pass through the data, our answer will be very wrong. This will be quantified in a loss function, and then in a process called backpropagation, it will adjust weights by assigning blame for the error backwards to neurons in the previous layers. The error, of course, is the difference between the output and the true label. Ideally, we'd like this error to be 0. The way that backpropagation works is to take the derivative of the loss function as a matrix of gradients that's applied backwards. Learning takes place over many forward and backward passes called epochs. If this learning sounds somewhat similar to the optimization we talked about in logistic regression, that's because it is similar, but on a much more complex scale. Here are some popular choices for activation functions for hidden nodes. The sigmoid, or logistic function, as you know, will output a value between 0 and 1, thereby normalizing the output of the neuron. The tanh function is similar to the logistic function, but centers its outputs at 0. This can be an advantage for modeling data with strong positive and negative values. The ReLU, rectified linear function, has been popular in recent years because using it makes training converge faster. It's linear from 0 forward, and then from 0 beyond to the left in the negative range, it's just leveled out at 0. To avoid overfitting, a regularisation term can be added to the activation function. This regularisation term is modified by another parameter, usually designated as lambda. As lambda gets larger, the coefficients of the activation function will shrink. The intercept doesn't shrink because the goal is just to reduce the coefficients, the absolute value of the coefficients associated with each predictor. 2 variations you see are L2 norm, which is quadratic, and L1 norm, which is a simple Manhattan distance. I have a couple of examples in the GitHub of using neural networks in sklearn. One is on the SPAM data set that we've seen before. I'm doing the same pre-processing, same train test split, and I'm importing the nlp multi-layer perceptron classifier. That's what sklearn calls its feed-forward neural network. Notice the solver is the same one we used in logistic regression. I have another parameter here called alpha. Let's take a look in the documentation. You can see there's a lot of parameters you can choose here. The alpha controls the regularization, and the default is a small value. I don't think I changed it very much. Specifying a random state will help me get similar results every time I run this notebook, because recall that the initial weights are random. This is the most important part right here, and this is specifying the architecture. I've requested 2 hidden layers. Notice you request those in a tuple. And the first one will have 15 nodes and the second one will have 2. It's using ReLU activation by default. Sometimes you may have to adjust max iterations. By default it's 200. So that's referring to the forward-backward passes. If it doesn't converge within 200, you might get an error, so you can always bump this up. To see what's going on, you can change this verbose to true, and you can kind of watch it learn. So it trained fairly fast. This is a smallish data set. And it got 98% accuracy and a higher F1 score than in the earlier algorithms we looked at for naive Bayes in logistic regression. So we got good results there with a minimum amount of work. That won't always be the case. Let's look at this multi-class classification example on the 4 topics from the 20 news group data. Again, same pre-processing we looked at before. I chose an architecture size of 15 nodes in the first layer, 7 in the second, and we got an overall accuracy of 86%. Recall that logistic regression got about 90%. So this neural network took longer to train and performed worse than logistic regression. You probably won't get lucky straight out of the box because you have to determine the architecture. So I tried many different networks. You can see the tuples here of the different network sizes that I tried. This is a situation where a pipeline might be useful. So I didn't do that here. I just reran the notebook with plugging in different architectures. But you could run a pipeline through several of these different neural networks with different architectures, then set it to run, go off, do something else, come back in an hour and see what happened. So we've seen how to do neural networks in sklearn. However, keep in mind that it's not really designed for large data. In the next chapter, we'll look at deep learning with the Keras package, which is a more robust implementation of neural networks. I just realized that I haven't been leaving you with quotes lately. Here's one from the character Sherlock Holmes by Sir Arthur Conan Doyle. It's a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts.